In this sequence of videos, we're going to really do a deep dive into regression. So we'll start off with a quick recap of a topic we didn't get to in Bayesian inference, and then we'll do some review talking about like what is regression, what is like 1D regression, multiple regression, like quickly recapping the ideas that you've seen in a class like Data 100. And then from there, we're going to dive in on the Bayesian perspective to regression. We're going to think about, okay, let's think about like these likelihood models and let's try to get a posterior for the coefficients in my regression model and say, what do I think that the distribution on the coefficients is? And we'll go through an example that we'll model a few different ways with a few different likelihoods, see what comes out, different posteriors, and we'll use that to develop this general idea of something called a generalized linear model, or GLM. And a GLM is sort of a way of thinking about, well, okay, linear regression, it's great. But what if we have some kind of like nonlinearity or some kind of like, data that we want to model that isn't real numbers? And you've already seen this with logistic regression. So we'll go through, we'll develop that idea, and then we'll circle back and talk about how do you implement that in the frequentist world. And that'll kind of set us up for next time where we'll learn about kind of like quantifying uncertainty, right? You get an estimate from regression. How certain are you? We'll talk about ways of seeing okay, like we're fitting a model, in this case, a bunch of regression style models. How good is that model? Does that model really fit your data? So we'll kind of build a foundation, diving deep into regression so that we can explore like model fitting, how good is the model, how do we quantify uncertainty going forward. Also, in this sequence of videos, we have some more detailed notes. So I really encourage you to like look through the notes, look through the notebooks. There's a lot more kind of like description and text around it. It's pretty similar to what I cover in the videos, but there's a little more there. So I encourage you to read through those, especially if you're the sort who would learn better through reading than through a video. In this video, we're going to talk about the posterior predictive distribution, which is a useful concept that comes out of Bayesian inference that's a little different from what we've been talking about so far. So we've talked about this idea of a prior distribution, which is like, what do we think about the hidden variables, the things that we don't know before we see any data, right? This is something we specify. We say, well, I think maybe they have this normal distribution, or I think maybe it's this. And then we have the likelihood, which is also something that we specify, right? We pick, well, I think if I knew the parameters, this is a distribution over the data that I'd get, right? I think that, like if I knew the means, then the data I get would be normal. Or I think if I knew like the probability, then like the poles would be a bunch of like a binomial sample. So that's the likelihood. It describes the probability of the data that I saw given the parameters. It's the distribution for that. And then there's the posterior, which is what we've kind of spent the most time on really like understanding and diving into, which is given that I saw the data that I saw, like I saw x1 through xn, now given that I got those particular values, what is the distribution over theta now, right? We sort of had the prior, which is like, well, what did I believe in the absence of any data? And then there's the posterior, which is like, what do I believe now after seeing the data? And now there's a new quantity that we're going to talk about called the posterior predictive distribution. And this is kind of different in character from any of the other things we've talked about, because what it is, it's really the distribution over the next data point that I'm going to see. It's xn plus 1. Like, what kind of data am I going to get in the future, given that I've seen a bunch of data so far? Now, why might this be useful, right? So this is like, what kind of data, if I saw this data, right? If I saw data, or if we saw data, then what kind of data might we expect in the future? Right? It's sort of thinking about, well, okay, like I saw these particular heights of people in this data set. Now, what happens if I see a new person? What kind of heights might I expect to see? I'm probably not going to see anything that's like, 9'4". I'm probably also, if I'm looking at adults, not going to see anyone that's like 1'2". So, there's some distribution over like reasonable values. And based on, the model that we had, like maybe, there's some values that are more likely based on gender and so on. But this is sort of thinking about what is the actual data that I'm going to observe going to be, right? You can think about in a polling setting, it might be like if I saw these polls, the posterior asks, what is the distribution over like the actual true percentage of people who are going to vote for a candidate? The posterior predictor distribution asks, well, what might the next poll be? What is the distribution of possibilities for the next poll? So that one might not be as useful. But another example from what you saw in lab is given that you did all these studies on COVID, right? We saw this example where for each of the studies, we estimated the SAR, which is like how much COVID spreads. And now the posterior predictive distribution says, well, what kind of data might I see in a new study? And that sort of by proxy kind of says like, well, what kind of data would I see in the real world, right? Like what are the possible spreads that I could see if I look at new households or new sets of households? So this is really a very different question. It's not asking, well, let's reason about like the hidden state of the world. It's let's actually try to like predict what's going to happen next. So this is an interesting concept. And how do we actually go about getting this, right? Because we have all these ingredients. Well, we talked about how the data are conditionally independent. So I'm going to say, well, we know how to like reason about the x's if we know theta, right? So, sorry about that. If we know the thetas, right, then we can like reason about what the distribution for xn plus 1 is going to be. And so what I'm going to do is I'm going to introduce theta and then I'm going to marginalize it out. So p xn plus 1 given x1 through xn is equal to, it's equal to that thing, the same thing, but also conditioned on theta times the distribution over theta, except it's not just like the plain old distribution over theta. We're working here in the world where we've conditioned on the x1 through xn, right? So like this quantity that we're interested in is conditioned on x1 through xn. And so when we introduce the distribution of theta, we also need it to be conditioned on x1 through xn. And now we just integrate out theta. Now again, this is like, wait, how do I do an integral over all theta? Well, it turns out that let's look at these quantities more carefully. The second quantity here, this should look really familiar. This is just the posterior distribution, right? This is exactly the same as what we've seen. It's like the thing we've been thinking about and like reasoning about for a while. What about this first term? Well, this first term says, what is the distribution for xn plus 1 given the first n data points and theta? Well, we keep making this assumption, and generally we'll continue to make this assumption that the data points are conditionally independent given the hidden variables. What does that mean? That means like if I know theta, then conditioned on theta, x1 is independent of x2. So if all the x's are independent given theta, then xn plus 1 only really depends on theta. It doesn't depend on any of these other x's. So this first term, by assuming that the data are conditionally independent given the parameters, this just becomes given p of x1, xn plus 1, given theta, right? So now this is a really interesting integral, right? This says, look at the, so let's actually just write out what the integral is, because now that we've simplified, because I think it's very interesting to think about. So this is like the integral, and if theta is discrete, it's going to be a sum. This is like distribution of xn plus 1 given theta times p of theta given x1 through xn d theta. And so conceptually, what does this mean, right? Like I wrote out this like integral with these like distributions, but conceptually, what does this mean? Conceptually, this says, let's think, so the thing I want is this right here, right? It's like, what do I think the next data point is going to be? And it's like, well, what would the next data, it says, what is the next data point? What could it be if I knew like this, right? What would it be if I knew what theta was? So let's think about like, pick a particular theta. Maybe it's like this set of values. Now, what is the distribution given that? Okay, now take that and weight it by the posterior on that theta. So if the posterior says like, yeah, that's like a really likely theta based on the first, n data points, then you're going to weight that one really heavily in your integral. Now let's think about like a different theta that's like, well, okay, maybe this one not as reasonable given the data points. And so this second term is going to be low. And then the first term is going to be kind of down weighted for that particular value, right? So we're kind of like averaging over all possible thetas, the likelihood for the new data point times the posterior distribution, that is how likely that is under that. Now, in practice, this integral is intractable. And so if we're approximating the posterior with, so there's two problems here, right? One is this integral is intractable. The second is the posterior is intractable. But we can do something clever, right? We can say, well, this term right here is actually an expectation, right? Like I kept talking about, like I talked about this average thing, right? This is really the expectation of P of xn plus 1 given theta, where this expectation is with respect to the posterior distribution. Or whoops, I messed that up. It's the expectation with respect to the posterior distribution. Why? It's because we're integrating a thing, and we're multiplying that thing by this distribution and integrating across all thetas, right? So it's essentially the expectation with respect to that distribution. So this is the expectation with respect to the posterior distribution of the likelihood for that new point. So what does that mean? Again, it means that we're like looking at, for every possible theta, what is the likelihood like? And we're kind of averaging across all of them. So why is this posterior predictive distribution useful? It's useful because it says, okay, now let me actually predict what kind of data I'm going to get in the future, right? In many applications, that's useful. It's also useful as a check on your model, right? So if you say, well, like I computed this posterior, does it even make sense? Like, how good is it? Well, you can do what's called a posterior predictive check. And we'll talk a little more about this later. But the idea is, like, let's say that you use your posterior to look at a bunch of samples out of this distribution here, right? Let's say like you do this, somehow by some witchcraft, you like get the distribution and you get a bunch of samples from it, right? Like it's like, well, maybe like the next X's are, these particular values. Now you can look at those values and you can say, well, how much are those like my original data points? And are they different in surprising or unexpected or bad ways, right? If those new data points kind of like seem reasonable given what you've seen so far, then it seems like, yeah, like you're in good shape. If those new data points don't look so good, then that might be a case for kind of like reevaluating your model, trying to find a new, better approximation of the posterior, changing your prior likelihood, and so on. Okay, so that's the posterior predictor distribution. It's like the distribution over the next data point, given the data points you saw. We saw that it's kind of like an average or an expectation with respect to the posterior. And since we can't compute the posterior exactly, we'll often approximate this with samples, right? If we have a bunch of samples, then let's say I have like 100 samples with different values of theta. I'll take each one of those, I'll plug them in. I'll plug in this term, I'll plug in this term, and then I'll multiply, I'll add them all up, and then I'll get the posterior predictive distribution. Okay, that's what it is. That's why it's useful. We'll talk a little more. In this video, we're going to review and recap a lot of the fundamentals around linear regression. So what is linear regression? It is a statement about, so remember in the simplest case, we have like 1D linear regression. So what we get is a bunch of pairs, x1, y1, x2, y2, and so on, all the way up to xn, yn. And so these are pairs, and these are all scalars, right? I have this little legend on the side. I'm going to use black for scalars. blue for vectors, green for matrices. So we have all these like pairs of points, x's and y's, pairs of numbers, or points, pairs of numbers. And each one, we're going to have this idea that we can somehow predict y using x, right? Maybe y is like how many copies of a book are going to sell, and x is like the number of pages of that book. Not going to be that good of a prediction, but we could try it. So the way we're going to do the prediction is we're going to set up this equation, and because it's called linear regression, it's yi is equal to axi plus b, right? So a and b are also scalars. They're just like numbers. So y is equal to some slope, a times x plus an intercept. So this is kind of your simplest setup for linear regression. And we know that the predictions aren't always going to be perfect. So we also have this idea of some error, right? So this is like the noise or the error associated with our prediction. So like y, we're trying to predict y, we have x, we do this. Okay, that's the simplest 1D case. Now, what about multiple dimensions? Well, now we don't just have a single x, right? Like you can imagine, let's say we're trying to predict how many copies of a book are going to be sold. Maybe we'd do better predicting if we didn't just use like how long the book was. Maybe we can also use like how many books has that author sold before, right? Maybe authors who sell more books are more likely to sell, their books are likely to do better, maybe, or maybe there's like beginner's luck. But the idea is that we have a bunch of features. So we're still trying to predict a single number, but now our pairs of our data looks like this, except now x, instead of being a scalar, is going to be a vector, right? So we have x1, y1, x2, y2, and so on, right? So we have a bunch of like these points where x is a vector and y is a scalar, right? So like you can imagine it's a vector where each entry is a different feature, right? Like one entry is like the number of pages. One entry is like how many books that author has sold before. Another, it might be, I don't know, like how high quality is the paper used to sell the book, stuff like that. And the thing we're trying to predict is yi is equal to beta transpose xi plus epsilon i. And epsilon is still a scalar, right? So we're still trying to predict y a scalar. We're still adding in some like scalar noise. And now the way we're thinking about it is that beta transpose xi, right? So this, what does this mean? This is like the inner product of two vectors. So this is really equal to the sum over j, beta j times xij. What is xij? It's like the jth entry of the vector xi, right? And so we're just sort of like taking each one, multiplying it by a beta, and adding them all up. Kind of like the one above, except a little more sophisticated. We're just like instead of just like taking the one number, multiplying it and adding it, we're taking a whole bunch of them, multiplying and adding them. Okay, so that's linear regression. Now we can kind of simplify this and say, well, okay, what is xi? Xi is equal to it's like x I1, x I2, and so on, all the way up to xid, right? Where d is a number of different features. In that example, the book example, it's 3, right? It's like the number of pages, how many books that author has written before, and like the quality of the paper, right? So in that case, there would be 3 features. D would be equal to 3. Now, x is a vector that has all these things in it. Now, we can also construct a matrix x, right? We'll usually use capital X for that, where we basically just like take all the xi's. Each one is going to be like a row of this matrix x. So we're just like taking all of the features for all of the data points and putting them together. So this is a matrix where we have x11, x12, and so on, up to x1 sub d, then x21, and so on, all the way up to xn1. And you can imagine the rest of the matrix. So now like going down rows, you're talking about different like data points, right? This is like each row corresponds to a different book. Each column corresponds to a different feature. Now, y sorry, y is not a matrix, y is a vector. We have the yi's, right? We can also make a vector out of those. So y is going to be equal to a vector of y1 all the way through yn, right? So this is a vector of, for every data point, what is the thing we're trying to predict for that data point? In the example with books, it's like for every book, we're trying to predict how many copies is it going to sell. And so that means that we can rewrite this equation here in vectorized form as y is equal to, y is a vector, is equal to x times the vector beta plus, and now we also have the vector epsilon, which is like, epsilon1, epsilon2, and so on. So we usually assume, this in linear regression, the simplest thing is we assume epsilon has a normal distribution. We assume that all the data, the epsilons are independent of each other. And in kind of like the classical linear regression setting, epsilon is the only thing that's random. Where in the frequentist world, we think of like beta as like a fixed but unknown thing that we're trying to estimate. We have y that's like random because of epsilon. X is fixed, right? There's no randomness in x, right? Like, because it's the data that we're using to try to like predict stuff, right? Like we're trying to predict, for a new book, we know all the x's, but we don't know the y, right? Like if an author is about to write, just written a new book, then I know like how many books the author's written before. I know like what quality paper I'm going to print it on. I know how many pages it's going to be, but I don't know how many copies it's going to sell, right? So y is unknown, but the x's are known. So the x's are known, not random. Beta is like unknown. In the frequentist world, random. In the Bayesian world, in the frequentist world, it's fixed. In the Bayesian world, it's random. Epsilon is always random. Okay, so that's the basics of linear regression. In this video, we're going to continue reviewing linear regression. So remember, we had this setup and we got to this equation y equals x beta plus epsilon, right? So this is an equation relating the vector y, the matrix x, the vector beta, and this kind of like unknown vector of noise epsilon. Now, we talked about, you've seen in the past thinking about these betas, like how do you actually interpret them? Well, let's think about the interpretation. So interpreting betas. Right, so let's go back to that example with the books. So we have beta 1, beta 2, and beta 3, right? If there's 3 features, then there's 3 betas. And so beta, let's suppose that they're in that order, right? It's like the number of pages, the number of books the author has written before, and the quality of the paper. So beta 1 tells you, in that case, how much y changes? Changes for each increase, each unit increase in feature 1, right? So like for, let's say beta 1 is like, I don't know, like 10,000. That means for every page that my book is longer, then I'm predicting that my book is going to sell 10,000 more copies. So based on that, like if my book is, like 20 pages longer, then I'm going to sell 20 times 10,000, like 200,000 more copies. I just made that up, but like that's the idea of what beta is, right? It's like how much y is going to change if you adjust the corresponding feature x. Okay, so that's how to interpret the betas. We talked about like the standard linear regression loss function, where so we talked about different loss functions you can use with this setup, right? So there's like the loss functions. So it turns out if you use the squared loss, or also known as the L2 loss, then you're looking at the loss for some prediction beta is equal to y minus x beta squared, right? So this is just, you're looking at this, and you're actually looking at not just y minus x beta squared. Why can't you square y minus x beta? because it's a vector, right? It doesn't make sense to like square a vector. So we're actually going to look at the norm of this vector. Remember that this like double bar notation means this is the norm of this vector. It's like you take every entry in it, you square it, you add them all up. And you divide by 1/n. Okay, so it turns out if you get this loss, use this loss, you end up with the formula that your prediction for beta hat is equal to x transpose x inverse times x transpose times y. For review, you can check out the Data 100 textbook, but you usually don't have to know this formula. There's like tons of software packages that implement it for you, but this is what comes out, right? You get some prediction for beta. And why is that useful? It's because you can interpret it this way. You can use it to like multiply by a new x to predict what the y is going to be for that new value. That's what you can do. Now, this squared loss function corresponds to using a Gaussian likelihood for the data, right? This corresponds to saying, I think that epsilon has a normal distribution with mean 0 and variance sigma squared I. Why am I putting an I in there? It's because remember, epsilon is an entire vector of errors, right? It's not just one. So I need to have this. I'm saying it's the identity matrix because they're all independent. So epsilon is a bunch of these noise terms, and that means that y, if I think about this from a probabilistic standpoint, that y is normally distributed with mean x beta and variance sigma squared I. And this is the n-dimensional identity matrix. So this is sort of thinking about, okay, y has a normal distribution. Centered at x beta, equally likely to make bigger or smaller errors, right? So this likelihood model corresponds to the L2 loss. And so you can kind of like think about it from a more like Bayesian probabilistic point of view and say, aha, like, this, or even frequent, it's like more probabilistic point of view. Like if I think about this likelihood function, I get this loss. They're kind of linked, right? Different loss functions also correspond to different likelihood models. We also have seen regularization, this idea that, well, there's like ridge regression, which you've seen, which is your loss becomes y minus x beta, the norm of that, but it's also, you also add in some constant times the norm of beta, right? And why do we do this? It's because, well, like, the idea that, well, we don't want the like term in beta to be too big, right? Like if your betas are too big, then you might end up overfitting the data. So we want to kind of like shrink the vector beta. And so we add this regularization term. And you'll actually show in the homework that ridge regression is equivalent to placing a normal prior on beta in the Bayesian world. Okay, so that's linear regression. In the next video, we'll review logistic regression. In this video, we're going to talk about a Bayesian perspective on linear regression. We're going to try to think about the standard, like y equals x beta. We're going to see how do we actually estimate the coefficients in a Bayesian way. And then we're going to say, well, okay, going beyond simple like linear regression with Gaussian likelihood, how do we actually do that in the Bayesian world? And we're going to list some examples with PyMC3 that'll kind of highlight how easy it is to kind of swap out different likelihoods for different data sets. Okay, so we have, remember the setup, we have this likelihood model, P of y given beta, which says if I know the coefficients, then what's my distribution over y? Notice that, I have y given beta. This also depends on x, but x isn't random, right? So I'm not like putting it behind the conditioning because it's not a random variable. I also have the prior P of beta, which is my belief about beta before I see any data. It's my belief about the coefficients before I actually get to observe any XY pairs. Now, in this case, we're actually going to ignore the prior. We're going to put a uniform, infinite uniform prior on beta. And you're probably asking like, wait, like that's not allowed, right? Because you have to have it integrate to 1. If it's infinite, then you can't do that and it's uniform. Turns out you actually kind of can get away with it. We won't talk about the details, but we'll see. They'll just things will just work out. Now let's go back to the likelihood because that's where I want to focus on today. So we have P of y given beta, right? And we've kind of seen the case where y given beta has like this normal distribution with mean x beta and variance sigma squared I, right? So this is sort of the standard least squares setup where we have some normally distributed errors that are independent for every observation. And this gives us the standard formula. But today I want to ask, well, what if the distribution for y isn't normal? Like, it probably makes sense if we're going to have a prediction that like the mean of y should always be x beta, or maybe some like slight modification of x beta. But what if like the errors, the noise isn't Gaussian, isn't normally distributed? So we'll talk through some examples of how we can do that. So let's make things a little more concrete and do some examples using PyMC3. So I have this notebook here, and I have this data set of wind turbines. Now, in this data set, I have one row for every state and every year. So for example, this first row says in year -3, which is, this is like number of years since 2000, in year 1997, Alaska built 6 wind turbines, which provided a power capacity of 390 kilowatts. And so we kind of can see like how many turbines got built, how much power did they provide, and this might be useful for prediction where we want to say, okay, like I'm looking at, like here's the number of turbines that have been built so far, how many are going to get built next year, how many are going to be there next year. And so let's kind of make our analysis simpler and just focus on one state for now. I'm going to look at Oklahoma. So I have this data frame called OK turbines. OK is the 2-letter code for Oklahoma, where I have the number that are built. And I also have the cumulative total, right? This is the cumulative number of how many turbines are there, how many turbines have been built in the past. So I can look at the cumulative total and I can look at a graph, and we can see the graph looks kind of like this, right? There's this sort of like rising pattern, and we can see, well, this looks like, more than just like linear, so linear regression might not be a good fit. Maybe this is like exponential. It looks like it's growing really fast year over year. So let's try an exponential model. So we can actually see how that might look by looking at the y-axis on a log scale, right? If we're saying like y is exponentiation of x, then that also means that x is log of y, right? We can take the log on both sides. So here you can see that the graph with the log y-axis on a log scale looks linear-ish, right? Like maybe it's not a perfect line, maybe it's kind of like tapering off, but it looks like exponential growth is really what's going on here. And this is kind of true of maybe not universally, but in the renewable energy world in general. Solar power, wind power is getting much cheaper. Everybody's building a lot more of it. Okay, so we have this data set, and I have the totals, and I also have this column log totals, which is just the log of this. So I have this, and now I'm going to do a Bayesian regression model. Let's actually start a fresh cell. So we have kind of similar to what we did before, what you saw in lab, where we have a model, but here instead of working with kind of like defining the variables like A is PM dot beta, Z is like PM dot normal, and so on. We're going to use this thing called glm from formula to do all the setup for us, right? This is going to say, okay, I have a model, and my model says that log totals is a linear function of year. This is sort of notation. If you've kind of done a lot of regression in R, you're probably familiar with this notation. If not, don't worry. This just means, like log totals is some linear function of year. If you have multiple models, you'd add them in here. And how does the model know what log underscore totals and year mean? It knows them because of this data frame, OK turbines, that I'm passing in. And that's the data frame that we just built up here. Great. So how does this work? Then we make our call to pm.sample, which actually goes ahead and runs the inference, right? So we can run this, and PyMC3 always takes a while to initialize, but then once it initializes, generally sampling, especially on a tiny model like this, is going to be very fast. especially because I only asked for 1,000 samples. So I can look at the output, which is the result of pm.sample, and you can see that it's sort of a souped up version of the trace that you saw in lab, right? There's like the posterior, there's like a bunch of other stuff, but what we're really interested in is the posterior, and it has these variables, intercept, year, SD. There's like something about chain and draw, like a bunch of metadata about it. So, I don't really like looking at numbers in a sort of collapsed thing like this. I really want like a visualization to show me what's going on here. And so I'm going to use this plot trace function that I call on the trace, and it'll actually draw out some nice plots for me. What do those plots look like? Well, I have 2 columns and 1 row for each of the variables it's predicting. What is it predicting? It's predicting an intercept, right? Because I'm in my linear regression in 1D, I have like y equals slope times the thing times year plus intercept. So here's what the intercept is. Here's what the coefficient on year is. And here's what the standard deviation of the errors is. So, and then over here on this side, we can see like this is the plot of like as the chain evolves. Remember, like with sampling, we're like how we have a Markov chain, we kind of like go from one sample to the next. This is how the value of the coefficient changes from sample to sample. So we have this coefficient on year, and it looks like it's centered around like, I don't know, 0.3, maybe like a little more than 0.3, but somewhere around there is where it's centered. So what does that actually mean? Well, it doesn't mean that like for every year we see 0.3 more wind turbines. That's obviously not like the case in the graph we saw. And why is that? It's because we log transformed the data, right? So let's think about like, so for every increase of 1 in year, we have a 0.3 increase in log of y, right? So y at, so like the number of turbines in 2021 is going to be equal to, well, the log of the number of turbines in 2021 is equal to going to be like the log of the number of turbines in 2020 plus 0.3, right? That's what this coefficient means, right? We increase the year by 1, the log of y, the log of the count goes up by 0.3. That's kind of what regression with log transformed y means. So we can, kind of like do some little bit of math on this. We can exponentiate both sides and see that this is equal to e to this something plus something else is like the e to this times e to that. E to the log this, the log goes away. So this is this times e to the 0.3. So what does this mean? It means that we have a multiplicative growth, right? And that's kind of how exponential growth works. It means we have this multiplicative thing going on where every year we multiply what came out the previous year by e to the 0.3. And what is e to the 0.3? It is 1.345. So what this is saying is that every year we have a 35% increase in the number of wind turbines. And that seems like a pretty reasonable fit to the model that we've seen so far. We can also ask, okay, so I have this 0.3, which is like, my mean of my sample, the samples for beta, the coefficient. But like, what if I, could have gotten something different, right? The whole point of the Bayesian formalism is that we can get some kind of like estimate of like the variability, right? It seems like, well, actually the coefficients, there's a pretty reasonable spread. Maybe it could be as low as like, I don't know, like 0.22, could be as high as like 0.37. So we can actually say, well, okay, what is x 0.22? What is x of 0.37, right? And that says, hey, the possible, this is a 25% growth year over year. This is a 45% growth year over year, right? So like, this is kind of the range. It's like somewhere 25%, 45% increase every year in the number of turbines. That's kind of what this model predicts. Again, like that still feels really abstract, right? Like, okay, 25%, but like, what does that mean? It was really helpful earlier when we were looking at the plot, the visualization. So let's actually look at a visualization of the uncertainty in these prediction lines. So I have this function, show posterior predictive. You don't have to worry about how it works, but it's essentially going to show me a bunch of possible lines that I could get, right? So like each one of the little gray lines is like a different sample out of the model with like a different intercept, different slope, and so on. And the blue points are like the actual data that I observed. And we can see that they're all like pretty reasonable, right? They all kind of like fit the data reasonably well. We see that there's something, like they're all like a little too steep. And the reason for that is, you should probably recognize by now that we have that outlier sitting at 2001 in the like bottom left side of the plot. And that's kind of like, kind of dragging the line down. But other than that, seems like, there's a reasonable range of possible samples. So that's kind of the standard Gaussian model, how we'd fit it with PyMC3. Next, we're going to talk about, okay, like what if that Gaussian model isn't the right fit, right? For example, the Gaussian says that the output is continuous and like we took the log, so it is. But like, wouldn't it be nice if we had something that just like models the fact that this is like a count? It's like a number of turbines. Like it can't actually have like 3.5 turbines. You have to have 3 or 4. And also, wouldn't it be nice to have something that models 0 as well? So that's what we'll get to next with count regression. So another way of looking at this problem is that the thing we're trying to predict is actually counts, right? Like we're trying to predict the number of turbines every year. And so instead of like taking the log and saying like that has a normal distribution, which works well and is a perfectly good approach to solve the problem in many cases, another way of looking at it is saying, well, what if I actually have some kind of distribution for y that is a distribution over discrete values that captures the fact that y is really discrete? And what distributions do we know over counts? Well, let's see, there's a geometric distribution, but that seems like a really bad choice, right? Because it's sort of like most of the weight is at the beginning. Another distribution for counts is the Poisson, right? The Poisson distribution is sort of like this. If you have some rate, then like how many times is the event going to occur within a window? That's one way of interpreting it. And so we can say, okay, let y be a Poisson have a Poisson distribution with mean x beta. Remember that the parameter for the Poisson distribution is that parameter is its mean, and the parameter has to be greater than 0. So problem is we can't just use x beta directly. We have to first exponentiate it, right? Because we need to make it positive. And how can we make something positive? Well, you could like take the absolute value. But exponentiating is nice because then that kind of has a similarity to what we did before, right? We took the log of y. But instead of taking the log of y, you could also like exponentiate x, right? If log of y equals x, then exponential of both sides, that means y is exponential of x. So let's make that a little more concrete. And we'll go back to this example we were doing. So we have y equals, we're going to say y given beta has a Poisson distribution with mean, well, it's not quite x beta, it's exp of x beta. And now this is our model, right? This, oops, I need to use this symbol. Y has a Poisson distribution with mean x beta. Great. And this is really like each individual yi. So I should really be using y sub I, and this should really be like xi transpose beta. Great. So this is my model, right? I have some vector of x's. I have some coefficients. I like multiply each one together, and I exponentiate that, and then y is going to have a Poisson distribution. Seems nice. Like now maybe I'll get some the thing I get out will actually be counts. So let's compare what we did before with what we're going to do now, right? So before we had this PM dot model, I called it Gaussian model. Now I'm calling it Poisson model. Before the formula was log totals is a function of year. Here I'm just doing totals, and the key is I'm adding in this extra argument family, and I'm telling it, hey, use the Poisson family for the likelihood, right? And PyMC3 knows that, hey, if I'm going to use a Poisson likelihood, then the thing I'm passing in has to be positive. And so it just knows that it better also do the exponential of this. I don't actually have to tell it. It just defaults to that. I could change it if I wanted to, I guess, but it defaults to that. And then the trace is pretty much the same as it was before. Great. So now we can run this, and it takes a few moments to run, and like we'll see we're sampling 2 chains, and it's running. And what is it doing? Again, it's computing the posterior distribution over beta. Why do we care about that? It's because, remember, one of the reasons we chose a normal likelihood earlier is like, well, like if the likelihood is normal, then the posterior is normal. Now, like if the likelihood is Poisson, what if the prior is normal? Like that seems really messy. But again, with the proximate inference, it doesn't matter what the distributions are. We can just throw computing at it and figure out the results. So this is taking a little longer to run. And we can actually look at the trace. So again, we'll use the same kind of function we did before. And we see that now we also get out a trace. Now, immediately looking at this, we see that something is very different, right? If we just sort of like squint at it from far away, like everything kind of looks the same, like the intercept has this, thing, and like the year has this thing. But there's this like mu, what's that? But there's something else that is really strange here, right? Let's look at the x-axis on this distribution over the year coefficient. It's way, 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 way narrower. Remember before I'm going to scroll back up to the previous output. This went from like 0.2 to 0.4, right? Which corresponded to like a 25% to 45% increase. Huge spread, right? Now, and we kind of saw that here. Now here, the range of possible values is really, 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 really small, right? The model is like super confident that the coefficient is pretty much exactly like 0.183. Very unlikely to have gotten a sample anywhere outside of that. And what does that correspond to? Well, that corresponds to about a 20% growth year over year. So the model says like, yeah, I know, like every year, the number of turbines is like 120% of what it was the year before. Pretty sure it's like, right on that. Now, why is the model suddenly so sure? Well, let's think about the assumptions that we're making when we use these models. So let's think about the normal distribution. What kind of assumptions are we making when we fit a normal model? Well, we're assuming that the variance, right? Like we're saying that the y has a normal distribution. And so that means that we're very unlikely to see things that are more than 3 sigmas away from the mean, right? Property of the normal distribution is like 68, 95, 99. So like most of the like mass of the normal is concentrated close to the mean. And that tends to make, regression with the normal distribution be kind of sensitive to outliers, right? That's why if we go back up, we saw this effect here. That's kind of a direct result of using the normal likelihood, is because, these lines like really don't like the fact that this error is like, we're squaring it, and like, we really don't want it to be very big. And so the line kind of like gets tilted towards that one line. That's kind of one consequence of using the Gaussian likelihood. What are consequences of using the Poisson likelihood? Well, if you remember some facts about the Poisson distribution, one of the most relevant here is that its mean is equal to its variance, right? The Gaussian, we have like 2 separate parameters, one for mean, one for variance. But the Poisson distribution has 1 parameter, right? And 1 parameter only, and that parameter controls both its mean and its variance. So when we're using a Poisson distribution, we're implicitly saying, hey, I think the mean of the data and the variance of my data are the same. So let's actually look and see if that's true. What did I call the y column? It was totals. So if I look at OK turbines totals, and let's look at the mean. Mean is this. Look at the variance. The variance is way, way bigger than the mean, right? So here, suddenly, this means that the assumption that the Poisson distribution is making is way, way off, right? The variance is like, like 4 orders of magnitude bigger than the mean. So definitely not a good fit to be using the Poisson distribution. And so what happens when I use this? Well, The Poisson distribution is assuming that the variance is equal to the mean, right? So the Poisson distribution is saying my likelihood has a really tiny variance. And so if your likelihood is like narrowly concentrated around the data that you got, then your posterior, which is proportional to your likelihood, right? Remember, like the posterior equals likelihood times prior divided by like stuff we can't compute. So if your likelihood is like really narrow and concentrated, like the Poisson likelihood is, because its variance is too low, then that means that the posterior is also going to be way too concentrated as well. And so this idea when your model is like assuming a really small variance, but your data actually has a much bigger variance, this is called over dispersion. And it's just a fancy way of saying that like the variances don't match and your model doesn't account for the variance of that. And what happens in this case, we see that the model is super overconfident. And we can see that if we do the visual representation with the Poisson trace. And if I look at the plot, it takes a moment to generate. You can see that for the Poisson distribution, we can see all the lines are like right on this curve. Remember, like in the earlier one, they're all gray, but here, like all the gray ones are kind of like stacked right on top of each other. And it's really sure that this is the exact line. But like looking at the data points, that doesn't really seem that reasonable, right? Like maybe it could be like a little lower, maybe it could be a little off. It probably, isn't as steep as this outlier would suggest, but, we really shouldn't have that much certainty. And so the Poisson distribution is not a good fit for this data because the mean and the variance aren't the same. So how do we fix it? Well, that's what we'll do next. All right, in this video, we're going to kind of go beyond Poisson regression for counts. We're going to talk about like where we've been, where we're going, and then kind of like figure out, okay, what's like the next thing, what's better that we can do. So remember, we kind of like had this idea we could fit linear regression. We're trying to predict counts of the number of turbines using like the year. And we said, okay, let's take the log of the count and use linear regression on that. And, that seemed to work reasonably well. But then we said, well, like the data, the number of turbines is a count, it's an integer. Can we use a distribution that actually models that explicitly? And we tried the Poisson. And, like in theory, it kind of like worked, but in practice, it really didn't work very well at all because it made this assumption about the variance, right? What we saw was over dispersion, which was a fancy way of saying that the Poisson distribution has like the mean and the variance as the same. It's sort of like a fundamental property of the distribution. But our data, the mean and the variance were not the same at all. The variance was way bigger than the mean, right? And so this is called over dispersion, where the variance of your data is bigger than the variance of what the model is assuming. And what that led to was like, a really like narrow likelihood because the variance is too small, and posterior is proportional to the likelihood. So like posterior was also really narrow. And it ended up being like super confident that, yes, like this is like the one true line in log space or like exponential curve. This is like the one true value. I know what it is, but we were like, well, but maybe it could have been different. So Poisson regression, not so good. So how do we fix it? Well, what we really want is a more sophisticated distribution that still looks at counts, still for like discrete values, but somehow has the ability to account for the fact that the mean and the variance might be different. And we already have this with the normal distribution, right? Like the normal distribution has two parameters, one for the mean and one for the variance. So what we want is like a discrete distribution that has the same properties, or not the same, similar properties. And what we're going to do is we're going to use what's called the negative binomial distribution. And there's kind of like two different ways to interpret this, or there's more than two, but the two ways that I think are most useful are, one, you can think of it as the sum of a bunch of independent geometric random variables, all with the same parameter. Remember, geometric is like the number of trials until you get one success. It's like you sort of like add those up, you get a negative binomial. Another way of looking at it is it's like a Poisson distribution, except if like you allowed some variability in the mean, right? You said like, well, the mean actually has some like variability, maybe it has like a gamma distribution or something. And so you have another parameter that controls like how variable that is. That's kind of a high level explanation. You don't have to understand the details, but it's a distribution over counts. It has more flexibility. I encourage you to actually just like, even right now, consider like pausing the video, taking a peek at the Wikipedia page for negative binomial, see what it looks like, look at, see the shapes of the distributions, and come back. Okay, so that's the negative binomial. And what we're going to assume is we're going to assume that yi is negative binomial, and its mean is going to be xi, there is one particular xi transpose beta. And again, negative binomial, like, it's a count, it has to be positive, the parameter also has to be positive. So just like before, we're going to exponentiate this. And remember that, if we exponentiate x transpose beta, that's like kind of equivalent to taking the log of y, right? Like you can imagine like taking the x of both sides of like of the top equation, or like taking the log of both sides of the last two, and you get something similar. So again, here we're both cases we're kind of like assuming this exponential thing, and we also saw that there's this kind of like multiplicative effect, right? If beta, like it has some value, that sort of tells you that, okay, if x increases by this amount, then y gets multiplied by e to that amount. Okay, so that's enough talking about it. Let's actually implement it and see how hard it is to write up the code. So one beautiful thing about doing this in PyMC3 is that, like the negative binomial distribution has this like, really complicated looking form. It has, well, actually, why don't we take a look at it? We can look at the distribution itself. So, like there's a bunch of different parameters. It looks like this. For k, the value, it's just like k plus r minus 1 choose k, 1 minus p to the r, p to the k, very complicated, involves this binomial coefficient. Looks like kind of a mess to work with. Imagine trying to do like the algebra of like computing the posterior for this. It would be very hard, very tricky, very annoying. But thankfully, thanks to PyMC3, we don't actually have to do any of it, right? It takes care of all of the gnarly work for us, both using approximate inference, which, we only have to specify the distribution, but also like it takes care of all the math, right? And you've seen on the homework that like computing the, derivations for these things can kind of get pretty hairy sometimes. And so it's really nice to have these packages that do all the hard work for us. Okay, so that's Poisson regression, like what we did before. And now this is negative binomial regression. And all I'm going to do is I'm going to change my variable name so I can keep track of things. So this is now negative binomial trace. And all I do is I change the family from Poisson to negative binomial. Boom, done. And now I run this. And, it takes a minute, PyMC3 starts running sampling using this no U-turn sampler nuts algorithm. Generates a whole bunch of samples for me pretty fast, prints out maybe like a warning or two. In 10 seconds, I have my answer. Great. And so now we can do the same thing we did before and look at the results. This is the negative binomial trace that I want the plot of. And you can see that now we have 4 plots instead of 3, right? Because there's like an extra parameter for the negative binomial. But again, the one that we're most interested in is this coefficient on y. And we can see here that it has this like, well, it doesn't really have a very normal E shape. It's a little too wide for a normal distribution, but it has this kind of like, there's like a central, like most of it's concentrated there, and then it kind of tapers off. And we can see that the mean is, I don't know, maybe like 0.24. So if we look at this, x 0.24, we're saying that this corresponds to a 27% growth rate, right? That means like every year, the number of turbines increases by 27%. So this is what we get from negative binomial regression. And again, seeing this like 27%, okay, a number, whatever. Let's actually look at the graph of like all the different possible lines that could come out of the model. So if we do, go back to this. And this is like, remember, this is the one from the Gaussian, just as a refresher. And then the one from the Poisson looked like this. But let's actually do this one. The trace. And what we get is a bunch of lines. And I actually like this even better than the one from the normal model, right? Because it sort of ignores this outlier from 2001 where there was like only one turbine. I guess Oklahoma was like just starting to build, and actually gives you a much better sense of like, okay, since then, here's the growth, here's the range of possible lines. Assuming that this like exponential model is a good fit, I think that these lines kind of capture the range of possible variability, right? There's sort of like, well, some of them are a little lower, some of them are a little higher. And so this is kind of the win with using count regression is it's really a good fit for this particular data set. And we saw that all we had to do was just change like a few lines or not even like parts of lines of code to get it. Okay, that's negative binomial regression. And next we'll talk about, okay, like we've seen a few different of these. Let's think about how do we generalize? What are the patterns that we're seeing? All right, in this video, we're going to talk about the big idea behind all these different kind of models we've been talking about and introduce an idea of generalized linear models. And I'll explain what that means in a moment. Okay, so remember we talked about the linear model. We talked about this Poisson regression. We talked about negative binomial regression. And just to make things simpler, I'm going to like talk about these in the abstract now, not about the specific example. And so I'm actually going to just talk about the linear model for a particular value, not log transform. Okay, so that's linear regression, Poisson regression. We still need the x because Poisson parameter has to be positive. Same with negative binomial. And also there's more parameters here, but we don't necessarily want to worry about them. And let's talk about a fourth example, which is logistic regression, right? So this is something you've seen before, right? How do you do logistic regression? Well, again, you do the same kind of thing where you look at xi transpose beta, right? You like take each of your features, each of your predictors, multiply by them by something, add them all up. And then you have this sigmoid function that you use on this, right? So the reason we did the x in the previous two examples was to like get something positive. And again, the reason we use a sigmoid function is because we want something between 0 and 1. Why do we want something between 0 and 1? It's because it turns out that logistic regression is equivalent to having a Bernoulli likelihood with parameter equal to this, right? So this is basically saying this is logistic regression, right? Remember that cross entropy loss function looks kind of similar to the like log Bernoulli likelihood. You'll actually work with this in discussion. But for now, take my word for it that this is an alternate way of interpreting logistic regression. It's saying if your likelihood is Bernoulli and you use a sigmoid function on your data, then you do this. So let's think about what all of these have in common. So what do all of them have in common? Well, for all of them, you're doing something similar, which is you're taking the x's, multiplying each one by a beta, and adding them all up, right? In most of these, it looks like x transpose beta. In the first one, it looks like matrix multiply x beta. So in all of them, we have the same kind of interaction between x and beta, right? The interaction is linear between x and beta. So that's common between all of them. Another thing that's like kind of different, but the pattern is the same for all of them, is then we take that linear thing, like, multiply each x by a value and add them all up. We take that, and then we kind of like pump it through a function, right? The second two, like I've highlighted that it's the x function, and the last one, it's the sigmoid function. And this one, you can kind of think of like, well, it's the like do nothing function, right? It's sort of just like take x beta and use it as is. The last thing that's again like a pattern, but it's different for every one, is the distribution that we're assuming for the likelihood, right? So in the first one, we assume a Gaussian likelihood. Second one, we assume a Poisson. Third one, we assume a negative binomial. And fourth one, we assume a Bernoulli, right? So for each one of these, we're kind of like, we have a different likelihood. And so all of them, we do like the same linear interaction between x and beta. Then we have some function that we compute of the results. And then we have some likelihood that tells us, okay, that, function of x transpose beta is the mean, but then like, what's the spread of the distribution around it? What kind of distribution is it? That's the likelihood. And so this pattern actually is a really powerful idea. And it's something that people have given a name for. And that name is generalized linear models. So these are 4 examples of generalized linear models. And like writing that out is kind of a pain, so people always just abbreviate these as GLMs. So remember like when we were using PyMC3, the package was called GLM? Yeah, that's why, because these are generalized linear models. And so for each one, what changes? Well, the things that we have to pick are like what's highlighted in yellow, which is like what function of x beta do we do? And then we also have to pick a likelihood function. So for this one, the likelihood function is the function we're using is the x function. And because just by convention, this function is called the inverse link function. So like in the thing I've highlighted in yellow, that's the inverse link function for all 4 of these. So we have, well, actually, let me just erase this so we can draw columns. So we can make this into a table where we have the name, we have the probability model, and we're going to have the link function, and we're going to have the likelihood. So by convention, the link function is actually the inverse of the thing I've highlighted. So what's the inverse of the x function? It's log, right? So in this case, the link function is log. In the first example, the function is just like identity, right? We didn't actually do anything to x beta. And so inverse of identity is just identity. So this is identity, the identity function, log function, right? So these are like different functions. The third one is the same as the second one. It's the log link function. And the last one is the sigmoid is the inverse link function, right? Like what I've highlighted. But the inverse of the sigmoid is called the logit function. So remember that the sigmoid looks something like, if you have something between 0 and 1, it looks like this. And so that means its inverse, the logit function, looks sort of like what if you have, so the x's become y's and the y's become x's. And so it looks something like this. That's called the logit function. Okay, so those are our link functions for these 4 examples. And then we have likelihood models, right? And again, here the likelihood is normal. Oops. Here it's Poisson. And here it's negative binomial. And here it's Bernoulli, right? So this is sort of just like 4 different link functions, 4 different likelihood models. You can imagine mixing and matching any combination. Well, not any combination because, like certain distributions need their parameters to be positive and so on. But you can do a lot of mixing and matching. You can choose whatever suits your data the best. And so this idea of a generalized linear model where you pick a link function and you pick a likelihood model, and then boom, you get the rest for free. And those like families that we saw in PyMC3 were just like basically packages that had like a link function and a likelihood like bundled up and ready to use. So this idea is very powerful. It's a very common thing you'll see with generalized linear models. And we've been talking about it from a Bayesian perspective, but there's nothing inherently Bayesian about like doing regression with like a particular function and a particular likelihood, right? We've actually seen that there's an equivalence between which likelihood you choose or like which loss function you optimize, right? There's sort of like a direct correspondence between those. And so it turns out that you can take all this and interpret this from a frequentist perspective as well, right? So we're thinking about, in this table, I have it in terms of like the likelihood. You can just as easily write like the loss function, and there's like a loss function corresponding to each of the likelihoods. And in the next video, we'll actually do some examples looking at the models we've seen in a frequentist setting using a different software package. All right, in this video, we're going to talk through implementing the same kind of generalized linear models that we have in kind of the Bayesian setting, where we kind of like built them up, looked at the output, thought about the ideas behind them. now we're just going to do a quick run through of how you do the exact same thing in the frequentist world, right? Like there's nothing like fundamentally like it has to be Bayesian to do regression, right? Regression is a concept that exists both in the frequentist and the Bayesian world. In the Bayesian world, we kind of like think about like, oh, like here's a different likelihood, here's like the posterior, here's these like samples, here's this, uncertainty, here's this distribution. In the frequentist world, we get an estimate, but we can still like quantify the uncertainty, right? Remember that we have things like standard error, we have things like bootstrap, we have ways of quantifying what the uncertainty and variability are, right? It's not like frequentist methods can't do that at all. And we'll actually see how we do exactly that. So I'm going to be working with the same data set of turbines in Oklahoma. And here I have this code from a package called stats models. And what I pass in is I pass in the y variable, I pass in all the x variables, and I tell it that, hey, for this one, I want to do a Gaussian model, right? So this is kind of like the same version that we did the first one, where we did like the log of the counts and we're fitting a normal model to that. And if I do this, then I can see that, boom, like, it just pops out results. We see that there's one parameter that comes out. It has some coefficient. It looks a lot higher than the coefficients we saw before. And also, if you remember before, there were like, even in the bare minimum, there were always at least two parameters, right? There's like the intercept and the slope. So this one is missing an intercept. And so we actually need to use a stats models feature called add constant, where we call add constant on this. And now we create this model, we call .fit, and then we look at the summary. And now we see that, okay, the coefficient on year, right, the coefficient for year is equal to 0.3, which kind of matches up with what we did before, right? If I scroll way up to when we were looking at the Gaussian model, right, we kind of saw that the mean of this was like around 0.3. So we get a very similar result, which for the Gaussian case definitely makes sense, right? Because the posterior is exact. So we should be getting pretty much exactly the same result. And just as a refresher for the Poisson, it was like 0.183. For the negative binomial, it was like 0.24. So here we get similar result to before. And let's take a look at all this other output, right? It tells us the dependent variable is totals. In this case, it's log of that, but yeah. It's a GLM model, generalized linear model. No, GLM, not GLM model. The model family is Gaussian. The link function is identity, right? We talked about the link function is like what you do to x beta before using it to predict the output. Method is something called IRLS, iteratively reweighted least squares. Date, time, number of iterations, covariance type, bunch of stuff. And then there are these interesting values here that we're not going to talk about right now. There's like log likelihood, deviance, and Pearson chi-squared. And these are all kind of ways of quantifying how well this model fits the data. And we'll actually talk about those in a future video. So, but for now, I want to look at, okay, there's this coefficient and there's this standard error, right? The standard error, remember, is the standard deviation of the distribution of the parameter, right? So remember, the coefficient on year is based on the data. And in the frequentist world, the data are random. So any function of the data, like our estimated coefficient, is also random, right? And that random coefficient has some variability. And that variability is estimated by, is like sort of captured by the standard error. So now we have our coefficient, and we also have a measure of uncertainty around it. Now, what if we wanted to do the Poisson model? Well, we could do something similar. Remember, for the Poisson model, we didn't need to take the log because it just sort of assumes an exponential link function. And I'm just going to try this, and let's see if it works. Yes, it does, right? So great. It looks like it works. The model family is Poisson. The link function is log. It knew that automatically. Remember, the link function is the inverse of what we do to beta x. So like we take the x of it. So the inverse of that is log. And we can see that here the coefficient on year is 0.183. Again, very similar to what we saw when we tried this in the Bayesian setting. The standard error is also extremely small, which means that, again, this frequentist model is also saying it's super confident about that coefficient, right? So the problem with Poisson regression is a problem regardless of whether you're being Bayesian or frequentist. It's because fundamentally the Poisson distribution doesn't let you model a mean and a variance that are different. And so I really should have been changing this variable name here. So let's pretend I changed that before I ran it. But okay, so this was the Poisson model. And we can also look at the negative binomial model, which is this. Oops, I didn't change all of them, but that's okay. So we have this, and now instead of Poisson, we're just gonna try. Can I just like write this? Do I even need to look it up? And yes, it turns out that that's exactly right. Great. So now the model family is negative binomial. The link function is log, and the coefficient on year that I get is 0.24-ish, right? And now we see the standard error is again like 0.04, meaning that there's some variability. So we get pretty similar results to what we saw in the Bayesian world. Again, we just sort of looked at things from a frequentist perspective. The standard error helps us quantify uncertainty. We'll talk a little more about like how we use that, what it is later. And we'll also talk more about these like ways of quantifying how good the model is later as well.